So we want to review bond polarity, finishing up chapter 1. And the nice thing about it is we start from Lewis structures. We can from Vesper, learn about 3D shapes. And then we can apply what we know about bond polarity to figure out the polarity of the overall molecule. And then that allows us to explain intermolecular forces. So the attraction between molecules, that will help us explain a lot of different things. So why we have solids, liquids, and gases, why we have differences in physical properties like melting points and boiling points. It all comes back to polarity. Why this guy, no matter how hard he tries, cannot jump through this wall, why a gecko can walk up a wall, and then things that are everyday things like why sugar dissolves in coffee. All this comes back to basic bond polarity. So I just want to quickly review the types of bonding we have. And remember that the difference in electronegativity between two atoms in a chemical bond is going to tell us what type of bonding we have. So if we have a very small difference in electronegativity between those atoms, we're going to have just pure nonpolar covalent bonding. Some good examples of this are going to be any atom that's bound to itself, right? We expect those electrons to be shared equally. One that I want you to write down or add here is that if I have a CH bond, carbon-hydrogen bond that we're going to see a lot in organic chemistry, it will also be considered a nonpolar covalent bond because there's not a very big difference in electronegativity between carbon and hydrogen. If we move on and we have a slightly bigger difference in electronegativity between those two atoms, we now fall into polar covalent bond territory. And some good examples that we're going to see in organic chemistry are carbon-nitrogen, carbon-oxygen, and any carbon-halogen bond. All of those are going to be polar covalent bonds. And then if we have, for example, a metal and a non-metal, now we have very different electronegativities, and that's going to be pure ionic bonding. So we can use all of this information and what we know about the individual bonds, and then we can put that together to see what's going on in the overall molecule. So let's look at some examples of that. Let's take, for example, water. We know that OH is definitely a polar bond or a polar covalent bond because oxygen is more electronegative. It wants those electrons more. So at any given time, because it's pulling more of that electron density to itself, it has a partially negative charge, and then the hydrogen will have a partially positive charge. So this arrow just shows us the direction of where those electrons are sitting most of the time. So this is our dipole. And notice that if we do that same thing for the other OH bond, the dipoles are pointed in the same general direction. And anytime they are, we can add those together. And so the overall molecule has a net dipole. And because it does, we didn't cancel the dipole out. The molecule itself is also polar. So it has polar bonds and the overall molecule is polar. And hydrogen, or water, does something interesting because of this. Since the oxygen has a partially negative charge and all the hydrogens have a partially positive charge, the oxygen of one water molecule can attract to that partially positive hydrogen on a neighboring molecule. And then you get a network of these, and this is called hydrogen bonding. Hydrogen bonding is going to allow us to explain a lot of different things when we get to intermolecular forces. So the first thing is surface tension. And surface tension, which is hydrogen bonding is involved in it, is responsible for all these different things. So why we have a meniscus here when we look at something like a graduated cylinder, why a water spider can walk across water, and why drops coming out of the faucet have the shape that they do. Let's look at another example. So this is carbon tetrachloride. It used to be used as a solvent pretty commonly, but it's a carcinogen, so it's not used so much now. But if we go ahead and draw first the Lewis structure, and then we can use Vesper to predict this tetrahedral shape, the first thing we know is that a carbon-chlorine bond, since it's carbon-halogen, it's definitely a polar bond. But notice in this case that all the dipoles are pointed away from each other. Okay, so in this case, even though we do have polar bonds in the molecule, they actually cancel each other out. They're all pointed in the opposite direction. So since we have no net dipole because of symmetry, the overall molecule is nonpolar. Okay, so polar bonds, but the overall molecule will be nonpolar due to symmetry. Another example of a nonpolar molecule is a hydrocarbon. So hydrocarbons only have carbon and hydrogen in the molecule. And we just learned that a CH bond is a nonpolar covalent bond. So if you only have CH bonds in your molecule, the compound is automatically going to be nonpolar overall. Okay, so we're going to learn that nonpolar molecules, along with all other molecules, have London dispersion forces that are very weak, but these very weak forces that hold molecules together, if you put many of them together, for example, the hairs on a gecko's hands and feet, that's what allows them to walk across or walk up a wall, because they're having these weak intermolecular forces between the hairs on their feet and the wall, but there are many of them. So predicting whether the overall molecule is polar or nonpolar, again, it goes back to 3D shape. So what we can do is we can look at the shapes that we've already reviewed and then predict whether the molecule is polar or nonpolar. Okay, and here are a few examples. So if I have something that has a linear shape around the central atom, so something like beryllium chloride, okay, we're automatically going to have a nonpolar molecule. So if these two are the same, so assuming that what's attached here is the same, I'm going to have a nonpolar molecule because I have symmetry. And even if these groups, if I have polar bonds here, they will be pointed in opposite directions, or the dipoles will cancel each other out. Another good example of this one is carbon dioxide. So I recommend drawing out the Lewis structure, drawing out the dipoles, and then you'll see that they cancel each other out. So it will be nonpolar overall. If we move on to where we have 3 bonds and no lone pairs, we learn that this is going to adopt a trigonal planar shape. And again, assuming that all of these groups are the same, so all of these groups in white are the same atom, the overall molecule will also be nonpolar. Okay. If we move on to methane, where we have 4 bonds, we have no lone pairs, so we know we're going to have a tetrahedral shape. It depends. So for methane, automatically nonpolar because I only have carbon and hydrogen, so it's a hydrocarbon. But let's say that one of these atoms were not the same. So they're not all hydrogens. Maybe I have 1 chlorine here. As soon as I throw off the symmetry, I now have a net dipole overall, and that would be considered polar. Okay, so again, if all of the groups on the ends are the same, it will be nonpolar. Whether those bonds are polar or nonpolar doesn't matter. The overall molecule will be nonpolar if all the groups are the same. But as soon as I have 1 or more groups that's different, now I won't have that same effect, and the overall molecule will be polar. So one example is methylene chloride. So CH2Cl2. If you could draw the shape, it still has a tetrahedral structure, but if 2 of these are hydrogen and 2 are chlorine, the dipoles will not cancel out, the overall molecule will be polar. If we move on to ammonia, where we have 3 bonds and we have 1 lone pair, we learn that this adopts a trigonal pyramidal shape, and we know that because the lone pair takes up a little bit more space than the bonds. In this case, we no longer have that same symmetry like we did over here. So if you have a trigonal pyramidal shape, it is automatically going to be polar because the dipoles will not cancel each other out. Same happens with water. We learned that if we have 2 bonds and we have 2 lone pairs, it's going to adopt a bent shape. And same idea, the dipoles, it will have an overall net dipole in the molecule, and it will be polar. All right. So again, everything builds on each other. We start with the Lewis structure always first. We figure out the 3D shape. We figure out if the individual bonds are polar. See if we have a net dipole overall, and then we can see if the overall molecule is polar. If it has a net dipole, it's polar. If it has no net dipole, it will be a nonpolar molecule. Okay, so I want you to review this, and then we're going to use this concept when we talk about intermolecular forces.